Hi guys. So today we'll talk about a very interesting topic that I haven't visited in a while. One of the viewers in the comments asked for this and I gladly agreed. Plus there's an interesting little bonus at the end for those of you who make it through this whole video. It's kind of a funny bonus and really cool website I found, or at least my geeky self finds it cool. Well, anyway, my name is Greg Fridman and welcome to my journal club. So today we'll talk about review of commercial nuclear fusion projects. So this is thermonuclear fusion, nuclear reactors, but fusion reactors. So this review is from 2023, so fairly recent. And this paper aims at giving a comprehensive overview of nuclear fusion concepts for industrial applications with a focus on the private sector. Now, before I go any further, I have to tell you, I've been skeptical of the nuclear fusion reactors. First time I heard about them was more than 20 years ago at a plasma chemistry conference in Italy. And one of the plenary lectures talked about, the progress to date, and, in 10 years, we'll see first commercial fusion reactor. And then, give or take 10 years ago, I heard in 10 years, we'll have a commercial fusion reactor. And a couple of years ago, I heard the same. So it is, it's a very grand goal. And if you don't know about nuclear fusion, it is an amazing dream. It'll give us free energy, basically. Not very free because reactors are expensive, but operating expense of this thing is very low. And it's often featured in movies like one of my favorites, Back to the Future. That's what the little surprise in the end is about. Anyway, let's dive right in. I think I have to read the whole introduction. It's really well written. Link is down in the description. I highly suggest the whole paper and look at the links. It'll take you back 100 years. Nuclear fusion have been investigated throughout the years since the first theoretical works on the star's core physics in the 20s and 30s. So we're looking at 100 years ago. The first machines to replicate fusion reactions on Earth were built around 1950. And both research and achievement have progressed steadily until now. Figure 1. So the green line way on top is the minimum requirement for this thing to be net positive in the power output. And if you look at from 1960s to today, only a couple of reactors even get close to an ignition where there's a tiny net positive outcome. Everything else before kind of sort of failed, but if you look at the trajectory over the last 1960s, so over the last 60 years, the trajectory is really promising. So it's very nice. Despite the physics and engineering complexity behind fusion reactors, nuclear fusion has always attracted mankind, thanks to the following key features. It achieves extremely high power densities, it relies on abundant fuel, and it does not emit any greenhouse gases during operation and shows a very low carbon footprint on a life cycle basis. It is intrinsically safe, thanks to the absence of chain reactions. So the reactions can't run away and explode like a nuclear reactor. The generation of high-level waste can be minimized by carefully selecting low activation materials when designing the reactor. And fusion power plants can, in principle, be designed for baseload production and with load-following capabilities. So you need higher load, you just crank up the reactor. And since the energy sector contributes to approximately 75% of the world's greenhouse emissions, not EVs, but okay. The introduction of high energy density, low carbon energy source in the energy mix would be an additional tool to meet the climate action goals and to improve the access to sustainable and modern energy. I mean, fusion is awesome. Me personally, I consider myself an applied scientist, and I focus on solving problems of today and maybe tomorrow. This is far bigger problem than I'm able to address. But kudos to those who are trying. Looks like we're close. And this paper provides a comprehensive, up-to-date 2023 review of fusion machine design in light of the tremendous acceleration that the nuclear fusion field has experienced in the last decade. Heard that one before. All right, so the structure of the paper, section 2 introduces the main applications of fusion energy and the challenges that are common among the different design. Section 3 provides a review of the approaches to exploit the fusion energy. Section 4 discusses extensively the main achievements. I'll blow over them. You know, if you want the details, please take a look at the paper yourself. It's pretty well written. It's a little lengthy, but it's worth it. So let's dive right in. Nuclear fusions, applications and challenges. Nuclear fusion, very briefly, you smack two atoms together and produce energy. So you fuse two deuterium atoms, they're isotopes of hydrogen. So you fuse two of them together, produce another isotope of hydrogen and a proton. Alternatively, you could use helium or boron. So I'm skipping a lot of the reactions. I don't think they're very necessary to the main point of this paper. So energy production. Nuclear fusion technologies find their main applications in energy production. The goal is to produce energy using the heat generated by nuclear fusion. So far, nuclear fission, so like the nuclear reactors we have today, has been successfully used to produce energy without CO2 or other pollutant emissions, but still faces issues such as production of high-level nuclear waste, the use of uranium that is not renewable, and a negative perception reputation that comes from exploding sometimes. These problems, the ones I just mentioned, are much less of a concern with fusion reactors. And as the authors already mentioned in the introduction, compared to other energy sources, nuclear fusion is cleaner, better, faster, cheaper. It just doesn't work yet, but once it will. Anyway, so for deuterium-tritium fusion, 80% of the energy is released as kinetic energy of neutrons. These neutrons, they do not interact with the plasma and escape the confinement. Therefore, only 20% of the energy produced in these reactions contributes to plasma heating. And external heating must be provided until ignition is reached. So we need to keep feeding electricity into this thing. There are three main approaches to produce energy from fusion reactions: magnetic confinement fusion, inertial confinement fusion, and magnetized target fusion. So MCF, ICF, and MTF. Magnetic confinement, inertial confinement, and magnetized target. Another application for fusion reactors is space propulsion. It's very cool. Nuclear fusion has a tremendous potential for space propulsion. Chemical propulsion has been successfully used in the past decades for short distance missions. You got to bring the fuel with. And the fuel is very heavy and you burn through it very fast. Deuterium-tritium fusion can be exploited to achieve higher specific power and higher exhaust velocity than nuclear fission propulsion by exploring known fusion processes and available technologies. Despite being less investigated than nuclear fission propulsion, nuclear fusion propulsion has been studied since the 50s within the Project Orion. It'd be cool. If we want to fly far, far, far away, we need to not be reliant on liquid fuel or uranium. Other applications, interesting, I haven't thought of those really. Nuclear waste processing. So you can feed nuclear waste into the fusion reactor and have it break down the reactants. and production of radioisotopes for medicine. So you can produce various isotopes for medical applications. Could be cool. And other applications of fusion include desalinization, district heating, and hydrogen production and process heat production, so just producing heat. So anywhere you need heat, you can use this reactor. Speaking of challenges, so you have this very hot thermonuclear plasma. You need to keep it away from the walls. If it touches the wall, it'll melt through anything. So to obtain an energy gain and a self-sustained system for fusion, plasma temperature and particle density must be tuned in a desired range. Maintaining this is called plasma confinement. The ions in plasma must overcome Coulomb repulsion by means of their kinetic energy to exploit the strong nuclear force that tends to bring nucleus closer together. Unfortunately, a strong nuclear force becomes dominant only in a very short range. So when the two atoms approach each other and two ions approach each other, the force keeping them apart is very, very high. How do you overcome that? Increase temperatures, smash them together faster. So the way all of this is achieved is high temperature and trying to confine the plasma, push it together. When you do that, you're squeezing an arc. There are various instabilities. The physics of these instabilities is beyond this paper, but dealing with them is one of the more challenging issues in fusion research. So you have this crazy hot plasma, very high temperature, close to those on a sun, that you're trying to contain, and it's moving really fast. It's basically a controlled explosion. So there are very, very many issues to try to do it carefully. Fuel is another challenge. So any device that exploits fusion reactions requires fuel and refueling. Current reserves of tritium are estimated as 30 to 40 kilograms total on planet Earth. As a means of comparison, a 3,000 megawatt fusion reactor would consume about 170 kilograms of tritium per year. So in just a few months, we'll run through all of the tritium resources on the planet. Therefore, we found a solution. You see, fusion keeps having issues, but very, very clever people overcome these tremendous obstacles by great ingenuity and complex solutions. So they use fusion device to produce or breed tritium in the reactor itself by exploiting the nuclear reactions between neutrons and lithium. Very cool. So you smash a lithium atom with a neutron, producing tritium and helium. And of course, lithium-ion batteries, lithium is everywhere these days, and available resources of lithium are more than enough to sustain fusion energy development at any reasonable rate for the next decades. That's good. There are other solutions like using different reactants other than tritium, like boron or others, and it just, for me, that adds further complexity to this development. Well, you have this arc that you're trying to squeeze together. Flowing arc has a magnetic field, so you can use magnetic field to control it, but you need big magnets. So in the majority of confinement approaches being currently pursued, the success of the project relies on the possibility of generating a precisely controlled magnetic field distribution, and superconducting magnets and coils are needed to obtain it in a cost-effective manner. In fact, resistive copper magnets can maintain very high fields, but the amount of power required to run them due to dissipation makes them not viable for a power plant design, requiring therefore use of superconductors. The high-temperature superconductor industry is relatively young and only recently is getting close to the point where it can ensure the production volume and the reliability of the product that are needed for a widespread employment of this technology. Everything is brand new. Like, they're developing technologies to solve the problems that fusion is encountering day by day. Moreover, the best arrangement of high-temperature superconductor tapes in cables and then in coils and magnets is an open field of research. So that even the research continues. So it's quite challenging. Also, this is nuclear fusion. There's radiation inside there. So materials operating within a fusion reactor will be exposed to a harsh radiation environment, depending on the region of the device where they will be employed, and mainly determined by long-term irradiation by high energy, up to 14 mega-electron-volt neutrons. So whatever you have inside the reactor, nearby the reactor, or even in the same building, needs to be able to withstand high doses of radiation to function for, a few years. You build a nuclear reactor, you want it to stand there for a decade or two or three. Another challenge is power conversion. So the main goal of a fusion device is to achieve net energy production, meaning produce more energy than you put into it. In deuterium-tritium fusion, 80% of the energy released by fusion is carried by neutrons in the form of kinetic energy. This energy must be first converted into thermal energy, which is achieved through use of blankets. So they put in this specially designed blankets that catch neutrons and convert their energy to heat. Another challenge. I wouldn't know how to do that. Another challenge is cost. Estimating the cost of the future fusion reactors is a challenging task for both analysts and companies. Nevertheless, there are no doubts that a fusion reactor and a fusion power plant will require huge investment. Huge. Preliminary estimates for the conceptual design of a reactor resulted in a total gross cost of approximately $5.5 billion. Similarly, US NASEM report sets as a target $5 to $6 billion for fusion power plant. The cost estimate for ITER, based on the 2001 design, was €5 billion, but the cost increased up to $20 billion, while some of the member countries are arguing that the final cost will be even higher. So this thing is really complicated and very expensive, but a lot safer than a nuclear reactor, so there are pluses. Major drivers for fusion reactor costs are the large size of the plant and the amount of raw material required, steel, concrete, etc. Need for specific components for which standardized production is not yet available, superconducting magnets, vacuum vessels, etc. And one can reasonably express a strong contribution from the capital cost due to the financial risk. So you're borrowing money to build this, and insurance for this will be crazy, because what if the thing blows up or ends up costing more than it should or never runs? It's a challenge. And it's a similar challenge to that new generation fission reactors, nuclear power plants, the Gen 4 nuclear power are facing. So on to commercial fusion projects. Starting with MCF, the magnetic confined fusion. Magnetic fields are a natural candidate for plasma confinement because the electrically charged ions and electrons that make up the plasma interact with magnetic field lines and follow well-defined orbits, avoiding contact with the reactor wall. For this reason, one of the key enabling technologies for MCF is that of superconducting coils. A superconductor can carry several orders of magnitudes more current density than a normal metal, and do so without any dissipation. However, the cables must be kept at cryogenic temperatures and have limitations on the maximum current and magnetic field that they can withstand. Figure 3. It's very cool. These things are running thousands, tens of thousands of amps per square millimeter. So you have a millimeter size wire running excess of kiloampere. That's pretty cool. Copper cannot do that. The reactor cost increases with reactor size. So because of that, compact reactors have gained popularity in the recent decade. However, there are 3 drawbacks when decreasing the reactor size. First, the confinement time is proportional to the reactor major radius. Second, the total fusion power is directly proportional to the plasma volume, hence the reactor size. Third, the wall and exhaust loading increase at fixed total thermal power, requiring the first wall and diverter material to withstand very high particle and heat flux. So you have all of these heat flux regardless of the size of the reactor. So it's tricky. You can make this thing small, but all of the supporting equipment will be the same as if you, or comparable, if you build it much bigger. So there's got to be a sweet spot, and it's difficult to find it without having, a dozen reactors of different sizes running. While the last issue requires advances in material science and engineering, the first two issues can be overcome by better performing superconductors that can produce stronger magnetic fields. Better performing than kiloamp per square millimeter. Cool, I would love to see that. This is amazing feats of engineering and extraordinarily challenging. So the paper goes into MCF type reactors. First one is tokamak, and tokamak is used by Commonwealth Fusion Systems. I'm not going to go into too many details. There's a demo DEMO reactor. There are stellarators, beautiful, beautiful reactors. If you have a chance to visit Princeton Plasma Physics Laboratories, look them up on their website. I'll try to remember to put a link down in the description. They do have public tours, and I went on one of those. They do show a stellarator. It is gorgeous. It is such a beautiful feat of human engineering. Try to put a picture in here. Let's see if I can find one. The Princeton Stellarator, that's the one I was talking about. And there's a link, princetonstellarators.energy. But see, I highlighted this. No public timeline is available. They don't know when they're going to finish it. So there's another company in Type 1 Energy. So there's spherical tokamaks. There's a company called Tokamak Energy. There are many configurations that have been investigated. In the past, some companies based the designs of their devices on configurations different from tokamaks, stellarators, or spherical tokamaks. Z-pinch reactors are really cool. Again, these are fascinating feats of engineering where you use interesting configuration of a magnetic field to kind of pinch this fast-moving arc. Next category is internal confinement fusion reactors. The most common approach in internal confinement fusion is based on spherical pellets heated uniformly by laser beams. So you take a spherical pellet and uniformly heat it with a giant laser. The energy burst ablates the outermost layer of the sphere, generating an inward shock wave that compresses the fuel with a consequent fuel temperature increase up to 1 to 10 kilo-electron-volt. The process takes place in extremely short times, just a few nanoseconds. And the plasma confinement is not improved by the presence of the external magnetic field. So you have a pellet of something and you shine a really powerful laser at it, trying to explode it to the point where you start nuclear fusion. That's one hell of a gun. That's for sure. First Light Fusion of United Kingdom approach to ICF exploits a high-velocity projectile instead of laser beam to compress fuel target to fusion conditions. The projectiles are accelerated in a gas gun. Read about light gas guns. While the target is embedded in a plastic block. So you shoot a pellet at a target at insane speed, far, far faster than any bullet can travel. Preliminary tests to validate the working principle have been performed on deuterium targets during an experimental campaign that comprised 21 shots. Back in 2022, this data was published. Measurements from the experimental campaign provide evidence of fusion reactions taking place during the experiment. Furthermore, 2 machines aimed at validating the accelerating system technology have been commissioned and built. The power plant will exploit deuterium tritium fuel and foresees a liquid metal first wall and a classical thermodynamic cycle to produce electricity. Operations will take place in pulse mode with an expected power output of 150 megawatt. No public timeline has been released by the company. So you're shooting bullets, pellets, at a target in vacuum fast enough, smashing hard enough to produce nuclear fusion, making 150 megawatt of power. I can't imagine how to build that. That's beyond me. I hope I will read about it in my lifetime, and it would be really cool to, toast my bagel using fusion power. Personally, I don't think it's going to happen, not in my lifetime, but I don't know. There is also magnetized target fusion, and it's comparable to ICF and MCF. It's pretty cool. General Fusion is a company based in Canada pursuing MTF by a mechanically driven liquid metal liner. The working principle is the following. Plasma is produced in a magnetized Marshall gun and injected in a cavity whose walls are made of liquid metal. The liquid metal walls are kept in position by setting the liquid metal in rotation inside the reactor chamber. Mechanical pistons surround the chamber and compress the cavity in short times, 100 milliseconds. Once the compression starts, the plasma is injected into the cavity. A linear compression ratio of approximately 10 along the radial direction is achieved in about 5 milliseconds, bringing the plasma to fusion conditions. Liquid metal being compressed as you add a thermal arc into this. Sounds complex. Sounds very complex. Then the liner rebounds and is brought back to the original position. The cavity is resetted and the process can be repeated. A mechanically driven liquid metal liner presents some advantages with respect to MCF or ICF devices. A liquid metal wall solves many issues that affect solid walls. Yeah, except it's liquid metal, like radiation damage, failures due to repeated thermal mechanical stress, and no risk of breaking during the compression phase. When was the last time you tried rotating the water around, a spherical chamber? How about really, really hot metal? This is tricky. It's amazing what humans can do, isn't it? The roadmap from General Fusion foresees the development and test of the main technology and physical process, plasma injectors, cavity and compression, plasma compression, liquid metal and materials, followed by integrated large-scale demonstrator and a commercial system. And when's that going to happen? Got it. And take a look at this paper. There's a number of companies doing this. And it's very curious to me. It's going to happen to this technology and how fast. We've been waiting for a while. So anyway, moving on to the discussion section. Despite the fact that this review focuses on private sector, and that certainly private initiative and funds played a pivotal role in this revival? I didn't know it died. An increase of dynamism in the nuclear fusion field, we want to stress that publicly funded research and projects are the basis on which these new opportunities stand. Ding, ding, fund science. And that the vast majority of the people involved in these companies come from academic world where they built the skills that they're currently employing for this commercial-oriented research. Huge investments are made into the private sector fusion. Let's take a look at Table 1. Commonwealth Fusion Systems. Total declared funding to date, $2 billion. CT fusion, mere 23 million, 97 million, 300 million, 4 million, half a billion, 1 billion, wait, how many zeros? 1,000, million, 1 billion. Who got 1 billion? Tay Technologies. The authors go into this very complicated matrix, that conceptual model for synergetic collaborations between private companies, governments, and public institutions. Yeah, if you're interested in how this whole thing is going to work, download the paper and read it. It's open access, costs you nothing. Authors touch on the geography of privately funded projects. Let's take a look at figure 5. So, geography of private companies involved in commercial fusion. Most of the companies are located in the US and more in general in Western countries. So, red depicts over 15 companies are in US, and a few, blue, 1 or 2 are in Canada, and maybe a couple are in Europe, China, Australia. Interesting. Timeline. The roadmaps proposed by private companies are in general way shorter than the ones indicated by the public research institutes. Well, duh. You're seeking investment, you want to tell them that, ROI, 10 years. I don't think so. Geography of public institutions involved in nuclear fusion research. All over the place. Lots in Russia, China, Europe, America is not lacking, so a lot of investment from the public sector. Technical maturity. Table 2, we attempt to give an indication of the maturity of each project. And I love this. Company, maturity. Technologies and proof of concept device being built and tested. Being built and tested. Technology concept formulated. Technology concept formulated, proof of concept devices being designed. Technology concept formulated. Back of the napkin still. Okay, very complicated back of the napkin involving supercomputers, I'm sure. But still, it's not yet, not yet available to purchase from your local electricity provider. And as final remarks, as a final word of caution, remind that technological and scientific progress doesn't follow a straight path, but rather rely on failures and mistakes to learn and improve. At this stage of great enthusiasm for fusion development, it is important to be aware that between current efforts and success, it is reasonable to expect a few snags and delays. A large fraction of the proposed design for ungreed fusion reactors will probably never reach the stadiums of prototypes. I like it, stadium of prototypes, leading to the convergence of the efforts on few solutions according to the natural selection of technology. The relatively large number of different designs currently under investigation is probably indicative of the immaturity of the fusion in general. In particular, considering that the debate is still on the more convenient physical process to exploit, for example, MCF, ICF, or MTF, and not just on engineering details. This situation can be clearly understood comparing fusion with a well-established technology like fission. Current nuclear reactors. While fission reactors can differ in many details, the fundamental physical process exploited by more or less all of the available facilities are the same. Conversely, in the first period of the human flight, airplanes and aerostats coexisted, and it was not clear what the winning technology would have been. So I think what the authors are trying to say is we're learning to fly, and we're not yet sure whether it's an aerostat or an airplane that, you know, first-class passengers are going to be boarding 20 years from now. So this is a really cool paper, and I greatly enjoyed reading it. Please, this was a recommendation by one of the viewers on the channel. So guys, ladies, if you have interesting ideas for me to look into, please mention it in the comment section below, or go to the Patreon page. I like to have these discussions over there. And finally, I was looking for a cover image for this video, and I thought of the old movie, Back to the Future. They used, I remember from the movie, last time I watched it, gotta be like 20 years. But I remember he dumps beer into the nuclear reactor of his car, a fusion reactor of his car. And I found this page. That's the picture. Yeah, Miller Lite being dumped into fusion reactor, and then he dumps the can in. But then this picture showed up on this page. Speculative identities. I'll leave the link down in the description. So this website is really cool. They look at speculative things mentioned in movies, and they analyze in great detail what the logo of the technology, Mr. Fusion, what does it mean, how it came about, talks about. It's a really cool website, great effort, and I didn't know this. The Mr. Fusion design is based on my favorite Mr. Coffee. That's pretty cool, and the logo is based on Westinghouse, I guess. It's pretty awesome, huh? Anyway, check out this website, really cool find, and it's a nice little bonus for reading this. Anyway, thanks, and see you guys next time.